Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss Laurent series. Let's begin. In the previous video, we studied about Taylor series. If a function f of z is analytic within a circle, then it can be expanded by Taylor series. But if that given function is not analytic within that of given circle, then we expand that particular function by using Laurent series. So what is Laurent's theorem statement? If f of z is analytic on C1 and C2, that is the annular region are bounded by two concentric circles C1 and C2 of radii R1 and R2, where R2 is greater than R1 and with center at A, then for all values of z in that of given region R, here circle C1, here circle C2, center at A, radius of circle C1 is R1, radius of circle C2 is R2, whereas R2 is less than R1, that region is the R, and that function is expanded as a0 plus a1 z minus a plus a2 z minus a square plus dot 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 plus b1 divided by z minus a plus b2 divided by z minus a square plus dot dot dot, whereas that section is written as an, the coefficients an is equal to 1 by 2 pi I closed curve integration over C1 f of w divided by w minus a to the power n plus 1 dw, and bn for that section 1 by 2 pi closed curve integration over C2 f of w divided by w minus a to the power minus n plus 1 dw. Now we have to prove the Laurent's theorem. Now we have take a cross cut AB. Therefore, that multi-connected region are now connected to a simple connected region. In that of simple connected region, the function f of z is analytic throughout that of given region. Now we can easily apply Cauchy's integral formula here. Now by Cauchy's integral formula, the given function f of z is expanded as 1 divided by 2 pi I closed curve integration over C1, first integration over C1, next integration over FB, integration over C2, also integration over BA, so on, that is closed curve 1 by 2 pi over C1 f of w dw divided by w minus z plus 1 by 2 pi I integration over AB f of w dw divided by w minus z minus, for anti-clockwise sense we treat as positive, clockwise sense treat as negative, from A to B taken as positive, from B to A taken as negative. 1 by 2 pi I closed curve integration, here we take negative C2 f of w dw divided by w minus z plus 1 by 2 pi I from B to A f of w divided by w minus z dw. that is equation number, okay. Here that AB and BA are cancelled out as we know it. Integral along C2 is clockwise, so that it is negative. Anticlockwise taken as positive. And integrals AB and BA cancelled with each other. Here the equation is termed as f of z is equal to 1 by 2 pi I closed curve integration over C1 f of w divided by z minus w minus z dw, next integral minus 1 by 2 pi I closed curve integration over C2 f of w divided by w minus z dw, that is taken as equation number 1. It has two integrals, integral 1 and integral 2. We can solve each integral one by one. For the first integral, f of w divided by w minus z can be expanded as like that of Taylor series, as z lies on C1, as z lies on C1, magnitude of z minus a divided by magnitude of w minus a less than 1, that series is converges equally. So, we can easily evaluate that particular integral. Therefore, although w lies on C1, due to that the first integral now converted to 1 divided by 2 pi I closed curve integration over C1 f of w divided by w minus z dw. It is expanded as 1 by 2 pi I closed curve integration over C1 f of w dw divided by w minus a. Taylor series is used here, plus z minus a divided by 2 pi I closed curve integration over C1 f of w divided by w minus a square dw plus z minus a square divided by 2 pi I closed curve integration over C1 f of w divided by w minus a whole cube dw plus dot dot dot. It has a naught plus a1 of z minus a2 z minus a square plus dot dot dot. that is equation number 2, where we prefer a nth is equal to 1 by 2 pi I closed curve integration over C1 f of w divided by w minus a to the power n plus 1 dw, where n starts from 0, 1, 2, 3 like this. First we put n is equal to 0. So, we have that resultant named as a1 a naught. Again n is equal to 1 a1, that integral is evaluated. Again n is equal to 2 and so on. In this way first integral is evaluated. Next, second integral we can expand. What is that second integral? In the second integral, z lies on C2. Therefore, as z lies on C2, from that of figure we conclude that the magnitude of w minus a is less than magnitude of z minus a. Therefore, w minus a magnitude divided by z minus a magnitude less than 1. So, now 1 divided by w minus z is written as 1 divided by w minus a plus a minus z. Just add and subtract a. W minus a minus z minus a. 1 divided by minus z minus a as common. We have 1 minus w minus a divided by z minus a. Taking z minus a as common in that of denominator side. Minus 1 divided by z minus a into 1 minus w minus a divided by z minus a to the power minus 1. We expand it binomially. Minus 1 divided by z minus a 1 plus w minus a divided by z minus a plus w minus a divided by z minus a square plus dot 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 up to it is continued as w minus a divided by z minus a to the power n plus 1 plus dot dot dot. Now multiplying by minus f of w divided by 2 pi I, we get minus 1 divided by 2 pi I f of w divided by w minus z, which is equal to 1 divided by 2 pi I f of w divided by z minus a plus 1 divided by 2 pi I w minus a divided by z minus a square f of w plus 1 divided by 2 pi I w minus a square divided by z minus a q f of w plus dot dot dot, which is equal to 1 by z minus a 1 by 2 pi I f of w. In that format we write all these terms 1 by z minus a square 1 by 2 pi I f of w divided by w minus a to the power minus 1, that w minus a to that of denominator side, it will be the power of minus 1, plus 1 by z minus a cube 1 by 2 pi I f of w divided by w minus a to the power minus 3 plus dot dot dot. Now we integrate that equation. Integrating we have minus 1 by 2 pi I closed curve integration over C2 here f of w minus z dw is equal to 1 divided by z minus a 1 divided by 2 pi I closed curve integration over C2 f of w dw plus 1 by z minus a square 1 divided by 2 pi I closed curve integration over C2 f of w dw divided by w minus a to the power minus 1 plus 1 divided by z minus a whole cube 1 divided by 2 pi I closed curve integration over C2 f of w dw divided by w minus a to the power minus 2 plus dot dot dot. It is written as b1 divided by z minus a, that term as b1, plus b2 divided by z minus a square plus b3 divided by z minus a cube plus dot dot dot, which is equation number 3, where we say bn is equal to 1 by 2 pi I closed curve integration over C2 f of w dw divided by w minus a to the power minus n plus 1, and that n continued from 1 to 3 like this. The two integrals as we represent in equation number 1 are evaluated as equation number 2 as equation number 3. Let we put the values of equation 2 and 3 in equation 1, substituting the values of both integrals from 2 and 3 in equation 1, we get f of z is equal to a0 plus a1 z minus a plus a2 z minus a square plus dot dot dot. Again from equation 3 we have the values like b1 z minus a to the power minus 1 plus b2 z minus a to the power minus 2 plus dot dot dot. In power series we represent that expression as summation over n from 0 to infinity a n z minus a to the power n plus these portions are represented as n is equal to 1 to infinity, n stands from 1 to infinity, here n stands from 0 to infinity, Bn divided by z minus a to the power n. This is the representation of a given function by using Laurent's series, as that given function is not analytic in that given region of a circle. This is the proof of Laurent's theorem. These two integrals are evaluated. First one expanded by using Taylor series, second one is expanded as usual method, that is represented by equation number 3. Putting the value of equation 2 and 3 in equation number 1, we have the required expansion of that given function, which is known as the Laurent series expansion. Next, two problems that is based upon Laurent series expansion. Expand the given function f of z, which is equal to 1 divided by z minus 1 whole into z minus 2 for z in that of given range 1 to 2. Here we take out the closed curve, concentric circles, let that point here 1, here is the point let 2, within that we have z. In that particular function, that function is not analytic at point 1 and 2. The given function f of z is equal to 1 divided by z minus 1, z minus 2. It is written as 1 divided by z minus 2 minus 1 divided by z minus 1. In the first bracket, let we take in the first bracket magnitude of z is less than 2. We take out 2 as common, and from the second one z is taken out as common, as given one is 1 is less than magnitude of z. Therefore, f of z is expanded as minus half. Here we have to take common 1 divided by 1 minus z by 2. In that of denominator, I take minus 2 as common. Two as common, a representation just like 1 minus z divided by 2. So, it will be that format, minus 1 by z taken as common in that of numerator of 1 divided by z minus 1. We have 1 divided by 1 minus 1 by z. It is in the form 1 by 2, 1 minus z by 2 to the power minus 1 minus 1 by z, 1 minus 1 by z to the power minus 1. Let me expand it by using binomial theorem. Minus half, its expansion 1 plus z by 2 plus z square by 4 plus z cube by 8 plus dot 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 minus 1 by z, that expansion 1 plus 1 by z plus 1 by z square plus 1 by z cube plus dot dot dot. Minus half is multiplied within that of bracket, the minus half minus z by 4 minus z square by 8 minus z cube by 16 dot dot dot. Again that bracket is expanded as multiplying 1 by z inside that of bracket terms, minus 1 by z minus 1 by z square minus 1 by z cube minus 1 by z fourth dot dot dot. In this way we expand that given function in that of region by using Laurent series. Next question, find the Laurent series expansion of the given function that is given as f of z is equal to z divided by z minus 1 into z minus 2, valid for z minus 1 magnitude greater than equal to 1, greater than 1. Solution, given function f of z is equal to z divided by z minus 1, z minus 2. Basically in case of Laurent series we use binomial theorem. It is easy and convenient to use binomial theorem for expansion of such type of series. Now we treat that function in the form of minus 1 by partial fraction method, z minus 1 plus 2 divided by z minus 2. Minus 1 divided by z minus 1 plus 2, that of numerator I take common as 2. Here z minus 2 is written as z minus 1 minus 1, there will be no such change. Minus 1 divided by z minus 1 plus 2 divided by, taking z minus 1 as common, we have 1 minus 1 divided by z minus 1 in that of numerator side of that particular term, minus 1 divided by z minus 1 plus 2 divided by z minus 1, 1 minus z minus 1 to the power minus 1, that term is expanded just like binomial theorem. So we have minus 1 divided by z minus 1 plus 2 divided by z minus 1, 1 plus 1 divided by z minus 1 plus 1 divided by z minus 1 square, 1 divided by z minus 1 cube plus dot dot dot. 2 divided by z minus 1 is multiplied within that of bracket, minus 1 divided by z minus 1 plus 2 divided by z minus 1 plus 2 divided by z minus 1 square plus 2 divided by z minus 1 cube plus 2 divided by z minus 1 fourth plus dot dot dot. In these two terms, minus 1 divided by z minus 1 plus 2 divided by z minus 1, we have 1 divided by z minus 1 plus 2 divided by z minus 1 square plus 2 divided by z minus 1 cube plus 2 divided by z minus 1 to the power fourth. The series continued. So that given function now expanded by using Laurent series. So with the help of this video lecture you understand Laurent series as Laurent's theorem, its statement and the proof of that Laurent series expansion, Laurent theorem proof. Its proof. Two problems related to expansion by using Laurent's series. So, with this useful and informative notes, let me wind up this session. Thank you.